Hello, everybody. Welcome to the Statistical Foundation on Reinforcement Learning. So this is our 12th lecture. So last week we've moved into the new chapter of the course, and we started to talk about offline reinforcement learning. And today's the first lecture after the short introduction last time, where we're going to be talking seriously about the offline RL. Okay, so let's get the lecture started. Um, yeah, so last time we finished talking about exploration under the linear MDP model. Like the last part of the regret analysis what was the uniform convergence of that um, inner product of the estimation of transition kernel with an arbitrary given um, state value function that we also estimated from data, and that was the reason why we need uniform convergence. And because we don't know like what that function is ahead of time, so we need to pre-specify a family of functions that always cover like this function that we have, and that requires us to take a union bound, or essentially take union bound over an infinite set sized space over a continuous space, function space. And the trick that allowed us to get around this issue of having to take the union bound over an infinite number of um, uh, probabilistic event is to use a covering number argument by actually covering that function space with that's infinite in size with a particular discretization, such that for every function within that function space uh, there is a center of this little ball in this cover set called epsilon net, that is epsilon close to this function. And then by something like a triangular inequality kind of argument, we were able to prove uniform convergence, therefore completing the regret analysis for exploration in linear MDP. Okay, then we give a short introduction to offline RL. So before we move on to talk about today's material, there is something about the exploration that I like to say that I didn't cover. Um, so in this course, we focus mainly on the theoretical driven techniques. So these are optimism. So the general principles of these methods still like apply to the more practical setting. Um, uh, yeah, they always apply to the more practical setting, but the specific implementation of that in modern deep reinforcement learning algorithms are could be quite different. So we talk about optimism and upper confidence bound approaches by theoretically proving that using this upper confidence bound suffices for us to explore in both the multi-arm bandit, linear bandit, and Markov decision processes. And the key trick is to add exploration bonuses. And these exploration bonuses are proven using such those uniform convergence stuff. Right, in the homework on the multi-arm bandit case, you'll see a different approach of balancing exploration and exploitation that doesn't really leverage optimism, but rather using an elimination type of approach that say like in some sense you're more closer to being pessimistic. And we also didn't talk about another powerful approach for exploration that is driven by some Bayesian model of the world called Thompson sampling, right? So this is something that typically works better than UCB in practice, and the theoretical analysis of this is significantly more difficult. And in practice, there are other like heuristic approaches for choosing the exploration bonuses, such as those curiosity-driven approaches, and also those um, 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 like instead of running the actual Thompson sampling, sometimes people promote exploration by adding noise to all aspects of a model. For instance, adding noise to the estimated model parameter before making decision, adding noise to the value functions directly before making decisions. Sometimes when the actions are continuous, you can directly sample actions from certain distribution. And these are some of the approaches that are used, and people try out different things and evaluate these heuristic approaches on um, experimental benchmarks, such as Atari games. And there are also a family of approaches that makes use of the model uncertainty. So this is in some sense a hybrid approach of the theoretical driven approaches and purely heuristic method that use, for instance, you could use bootstrapping to empirically estimate how accurate your model parameters are, and that um, sometimes could translate into valid exploration bonuses that helps you to estimate the model better in those regions where the model is currently very uncertain, right? So there's still a large gap between theory and practice, but the idea of exploration is usually driven by um, 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 the same principle of optimism in the face of uncertainty. Is a specific implementation of how you are going to be realizing these principles for exploration that differs in theory and practice. Okay, so last time we gave a quick introduction of the offline reinforcement learning. Let me just quickly ensure that everybody is on the same page. So in the online environment, reinforcement learning, the agent can interact with the environment by taking actions and receive the next state and reward, and then adjust the policy and take the next action. Right? In offline reinforcement learning, like you do not actually have online access to the environment at all. Instead, maybe somebody else, maybe this agent's cousin interacted with the environment for an extended period of time and collected some offline log data. And then this agent needs to just look at this log data to come up with the right policy. So when this agent needs to play in the future, and this agent will be able to start off with a policy that are better than starting with no knowledge at all. So how do we learn a policy from somebody else's collected data that were collected by running a different policy? So the two problems in offline reinforcement learning are the offline policy evaluation and offline policy learning. And the policy evaluation problem focuses on the problem of prediction. If you give me a target policy, and I simply would like to know how good the performance of this policy is, right? So suppose I have online environment, then I can simply run this policy and collect data about it specifically. But in the offline case, I don't have access to the online environment. I have to answer this counterfactual questions. What if I didn't run policy mu? Instead, I had been running this policy pi from beginning. What the performance? What the overall rewards that I would have collected by answering such counterfactual questions. Okay, the offline policy learning is more is a more challenging problem. It not only requires you to evaluate, like sometimes you don't even need to evaluate, but the ask about finding the argmax. It talks about how can I optimize the policy provably by not interacting with the world and only looking at the data collected previously by a so-called logging policy, logging policy mu. right? Sometimes it's also called behavioral policy in some contexts, which is reflected to the behavior that the agent took when collecting this offline data set. Okay, so we talked about the simplified model by getting rid of the dynamics. So the contextual bandits model is slightly more complex than the multi-arm bandit because they are now contexts, or in other words states. So these contexts, you can just think about these as state variables, but now by default the state variables they're continuous. And actions are we consider this to be discrete actions for now, and then rewards are drawn from some unknown distribution. So the expected reward, so the expected reward, yeah. So given state and action, right? So this is this R as a equal to little a as RSA function from Markov decision processes, right? So everything is the same except for the change, the slightly changed notation and the fact that we are sampling this sequence of state from a fixed distribution, fixed unknown distribution, rather than taking actions, and action will result in will change the distribution that we observe in the next state, right? So we have stripped out the dynamics. So this is a simpler problem that we can talk about. Yeah, throughout the lecture, I'll try to use the familiar notation by using such capital letter, capital SI, AI, RI, to denote the data that we collect that are random. And when you see like XI, AI, and RI, whenever there's an index I, so they refer to data, right? So in those places that I'm not in the already typesetted part of the lecture slides, you will see like lowercase letters denoting random variables. But I'm just asking you to, whenever there anything that's unclear in the set of notations and others, please alert me and I'll explain it. Okay, and whenever we see this isolated like little a and X and R, like whenever there is an expectation in front, then this means then this means the random variable, I guess S, is equal to this little s, and this means that the A is equal to the little a, right? And this part in the expectation, this needs to be the random variables. This is, I guess, R1, S1, A1, right? Okay, so let me change the color of this pen. So red is a bit. All right. Okay, so that was the setting that we consider, and we talked about two baseline methods for solving the off-policy evaluation problem for contextual bandits, right? So they are the first is the so-called direct method or regression estimators. So the idea is that you can use the data and fit a regression model, which uses the context and action to predict the expected reward, right? So R hat is fitted using the data, and then this from A to some real value, and the goal is to use R hat to approximate R of S A for all I say. And this is a supervised learning problem, right? Why is that? Because we have collected data of the form of state action pairs, and we also collected the resulting reward variable. So this is a regression problem, a supervised learning problem, and you can choose your favorite regression method, linear regression, decision trees, neural network, like whatever you want to set to instantiate this R hat, right? And when this R hat is an accurate estimate, then you can plug in this into whatever new policy that you'd like to evaluate, and average over the observed state. So this will be a good approximation of the expectation over X drawn from this lambda, and this part will be just plugging of the expected value of A drawn from the A drawn from the target policy given S Si or Xi, and reward of A given the observed X. Okay, just replace this with replace this expected Ri with this regression estimator. Okay, and the other idea we talked about is to use the importance sampling idea, or also known as inverse propensity score. So propensity are just probabilities. So they are the probability of taking this action AI. Then in this case, we are using this quantity called the importance weight to do a weighted averages of the observed reward. And we'll denote this to be rho I for the remainder of the lecture, right? But notice that rho I is a function of AI and Xi. Okay. Yeah, in this lecture, we're going to continue with these estimators and proposing a few more of them, and we'll talk about how do we evaluate these estimators themselves, and which one is better, which one is good, which one is bad, in what circumstances, and how do we improve upon this simple like importance sampling and direct method estimators. And we'll do some simple statistical analysis, like calculating mean, calculating variances, and comparing the different methods sometimes against their lower bound for statistical efficiency, right? And then we're going to derive the related estimators that extend this idea from contextual bandits to the reinforcement learning setting, right? So that's the plan for today. Yeah, any questions so far? Good. So hope the setting is clear. So the first thing we shall do is to analyze the performance of the importance sampling estimator. So what is it doing? Well, so let's first rewrite the importance sampling estimator. So this is VIS pi, and this is equal to you collect n data point, and in every data point you take action and collect some reward, right? So this will be AI SI. That's the probability of taking this action from the target policy. And in your logging or behavior policy, you have taken your action according to this probability. And then, so this is importance sampling estimator. So I've shown you last time that this is an unbiased estimator. So let's work out the math again. So we want to take the expected value of this importance sampling estimator, right? And the expectation is taken over the data that you have collected, right? So you can decompose this into the expectation over yeah. So first of all, by the linearity of the expectation, you can push this inside, right? You can push this inside, and this becomes the expected value of pi AI given Si, pi AI Si Ri, right? And since every data point is independent, then I can simply like estimate the first one of them. So I can choose I to be 1, right? It's independent to the index because every in expectation. So every time you collect data, they're coming from completely the same distribution. So I can further decompose this into expectation of S1 drawn from this distribution, and the expectation um, of A1 is taken according to this is new, according to the behavior policy. That's how your data is collected, right? In the like better mathematical notation, like I should use the conditioning towards the back, but that makes it slightly longer to write. And lastly, I'm taking the expectation of Ri given given S R1 given S1 and A1, right? And then I multiply this importance weight A1 S1 A1 S1, right? And given S1. Okay, and now let's start to simplify this. So this is just a expected reward. So this is R of S1 A1, right? And then we get then we can like expand on this expectation. So this is a summation over all the possible A in the action space, mu of A given S1 multiply with pi of A S1 over mu of A S1. And these two got canceled out, and what remains is R of S1 A, right? And then taking the like noticing that this is a definition of expectation for the policy on the pi, and also taking the expectation over the state that's outside, then we get the value of policy pi. Okay, so this shows that the important sampling estimator is an unbiased estimator, and the key idea is a change of measure using this importance weight. So how about the variance? So let's analyze the variance. So the variance of 1 over the important sampling estimator is slightly more complex, but it just follows from the same algebra that you have been practicing homework 0. So law of total law of total variance. So the first thing that we note is that this is 1 over n multiplied with the summation of independent random variables. So by the formula of variance, we can get this amplification factor out, and then consider the variance of just one of the data point. Right? And then we can apply the law of total expectation by expanding this variance into expectation of E of V and V of E, right? By conditioning on something. So yeah, I'll leave this 1 over n always in the outside. And this is the expectation of the variance. So let's maybe first condition on S1, right? So we first condition on S1. The first term is expectation of variance, and the second term is the variance of expectation. right? And the second term is something that we can already we can already deal with. So notice that inside this this expectation is taken is for mu, and outside this expectation and this variance is for the uh, for the state distribution, right? Right. So for the second part, we can already take care of, right? So let me write it in the end. So I'll have 1 over n. So let me write the last term in the end. So this is a variance of s, but inside you have this expected value, and since this expected value is a summation over mu will cancel out with a term in the denominator. So this becomes the expected value under pi, under the target policy of your reward, right? So R of S1 and A1 given S1. Okay, and so this part of the variance is coming from the variance of the state, right? And inside this is everything's taken out, and this is just expected um, uh, expected reward of taking policy pi at states at a particular given state. Okay, now for the first term, we actually need to apply the law of total expectation again, right? So let's do that. So let's further decompose the conditional variance inside the expectation into expectation of variance and variance of expectation. So so this time it will be expectation of A drawn from mu, right? A1 drawn from mu1 as S1, and then the variance will become variance of only that of the reward, right? This will be only that of the reward. So let me use this shorthand notation rho. Notice that rho is a function of S and A only, so it is a constant inside this expectation, inside this variance. And I can extract this out. I can extract this out with a square. Yeah, since this is a variance, and given S1, right? So let's call this let's give this variance a name, right? So this is a given state and action, the variance of the reward, right? So we can call this sigma sigma as a function of SA, right? So altogether, so this terms gives the expectation of rho square and R of S and A. Yeah, not R, sigma square. So let me write it more nicely. Sigma square S and A, right? And this is under the distribution of mu. And then the second part of this the second part of this is law of total variance is a variance of expectation. So we'll have the variance of also A1 drawn from mu S1, and inside this inside this is the expectation of rho 1 and R1, rho 1 R1 given S1 and A1, right? So what is this? Given S1, and then plus everything that's so the second term becomes the first of all expectation over and then the variance over mu, and inside inside. So this is simply R of S1A1, right? R of S1 and A1, and yeah, and rho is extracted out of this expectation, so you get rho1. Okay, so this is a part of the variance that yes. Okay, and let me just write the third term down as well. Okay, so now we have a three-term decomposition of the total variance, and in each one of them is highly interpreted, can be interpreted very easily. So let me just say again what this is. This is a variance that's coming. The first term is a variance that's coming from the intrinsic noise of the reward variance, conditioned on each S and A separately. The second term is the variance that's coming from your taking random actions, right? Suppose mu is deterministic, then this term is 0. But meanwhile, that will also imply that this rho is actually unbounded, right? So this is a variance that's coming from your policy. So login policies. And the last term, this is coming from the variance of the context. So recall that the context is drawn from some distribution that's out of our control, right? So these are the three parts of the variances that's affecting the IPS performance. So yeah, we'll see this again once we analyze the other estimator. Yeah, so while when we look at this page, it's a page of equations, then like the underlying idea is intrinsically simple, right? So we're basically applying a law of total variance and decomposing the variance into terms that makes it easier to interpret. Yeah, and what's important is that you always have a 1/n term in front. So as the number of data point goes to infinity, so as long as this rho parameter is not too large, and this will converge to the true value. Okay, but then what this is saying is that to compare the different estimators, we really have to compare the constant to see how the numerator on top of this 1/n term, how large or small they are. Well, so in order to compare with a multi-arm bandit, so let's maybe consider an simpler setting with instead of contextual bandits, let's simplify it even more and consider the multi-arm bandit, right? So this is an estimator for the contextual bandits. So when we go to the multi-arm bandit, so what we can do is to simply get rid of this xi, right? So get rid of this xi altogether. And then the standard estimator, the regression estimator becomes simply r hat of a pi of a, right? So, and this one becomes the simple importance sampling. Okay, so let's make this change, and then on this example, I'm not going to show you that these two estimators are actually very similar to each other. You can write each one of them in the others form. Okay, so let's consider just a multi-arm bandit. So how can we write the importance sampling as something that resembles a regression estimator. Right, so we had IS. So as we say, this is then importance weights multiply with sorry, I should be using a capital. Okay, so this is a importance sampling estimator, and in fact we can rewrite it as a summation of the different A in the action space. Yeah, we can just change the order of the summation, and then like write it in a slightly different way. And this becomes, if we collect all the AIs that are the same, so we will get the first of all, pi of A, and then secondly, summation of 1 over n summation of R I multiply with indicator AI is equal to A, and then divide by the mu of AI. Yeah, what this is saying is that you can essentially see that this is the same as a particular estimator, R hat IS, applying to a particular A. So what is this R hat? R hat IS of A? This is equal to, first of all, 0 if not really that, but yeah, you can do it that way as well. But yeah, now we're pulling all this one summation of 1 over n together. So this is equal to 1 over n indicator of AI equals to A over mu AI, right? Yeah, so it is an empirical average of an imputation of an imputed version of and this is equal to 1 over n sum of I of this R hat IS A given index I, right? So this is the imputed version of the reward, and this imputed version of the reward. So you can interpret the importance sampling as filling in the missing value, right? So in this case, if you consider only the ith data point, so this is equal to 0 if AI is not equal to A, and this is equal to a rescaled version of this of mu AI if AI is equal to A. Right, you can see that this alone is an unbiased estimator, and you are essentially doing zero imputation of those actions that you did not take by making the actions that you have actually taken larger by a factor of the inverse propensity score. Right, so like I hope that this makes sense. So now this becomes a vector, and this vector is your imputed estimator that applies to every individual data point that you collect I, and the only non-zero elements is the one that where A is equal to AI, and all the other places are 0. And this part, for this part, you are using Ri divided by mu of AI, and then put into this only non-zero coordinates of this imputation. Okay, and by averaging this vector, and you end up getting this regression estimator for that's coming from IS. So on the other hand, in the multi-arm bandy case, if we consider the natural regression estimator, we can also write it as an importance sampling estimator. So how does that work? So recall that we had pi of dm is equal to summation of a r hat of a multiplied with pi of a, right? So this is a regression estimator, and the natural way of constructing this r hat is by what we have seen in the multi-arm bandit literature by simply plugging, right? By simply using 1 over n a sum over Ri indicator and Ai is equal to A, right? Where if Na is larger than 0 and 0 otherwise, right? So if you have pulled this arm in your offline data set for at least once, then I'm just using the empirical averages of what I have observed as my estimator, and otherwise I'm just filling in some arbitrary number. So let's say that let's use 0. Okay. And if we substitute this into the formula of the direct method, then you can actually get 1 over NA sum over I Ri indicator of AI equals to A multiplied with the pi of A, right? And by writing NA to be the you can write NA to be n times the summation of indicator AI is equal to A divided by n, right? So you can write this, since this n cancels out, and this is equal to n times the empirical estimator of your behavior policy's probability distribution, right? So by substituting this into the above the above formula, you get A and 1 over n and 1 over mu hat of A and summation over I from 1 to n Ri indicator AI is equal to A and pi A, right? And by exchanging the order of the summation here, you can rewrite it as 1 over n sum over I from 1 to n pi of A over mu hat of A and multiply with R of I. Right, so this is an importance sampling estimator, and the only difference is that now the importance weight is instead of pi over mu, you are using the empirical estimator of this mu A, right? With the only difference being that mu A like cannot be 0, right? So you have to define this mu A appropriately when things are things are actually 0, right? So mu hat of A isn't 0. Yeah, and when it is 0, then this part of this R hat A applies, and then you basically deal with it separately. Okay, so I've shown you that importance sampling estimator is actually can be written as a particular way of unbiasedly estimating the regression function non-parametrically without assuming like any function form from A to R by just doing this kind of imputation. I've also shown you that the regression estimator, you can actually also write it as an importance sampling estimator by choosing the empirically estimated importance weight, right? So the key question to consider now is that which estimator is actually better. Like how do we analyze this? When should we use the importance weighting, and when should we use the regression estimator. So a key observation now is that the regression estimator now is actually having access to like a realizable function, like trivially, since this expected reward given action, right? So this is the function that we're interested to estimate. Since this thing like it's just a given by k statistics, where we can actually collect random samples from, then this way of plugging in this way of plugging estimator of this reward, actually as n goes to infinity, as this na goes to infinity, actually converges to R of a, right? So R hat of a actually converges to R of a as na goes to infinity. Right. So this is a case when we actually have access to some function, some regression function that's asymptotically correct. Okay. So we'll see how that how that helps us in dealing with this. Right. So we will compare the mean square error of like fairly compare these two estimators using a metric called mean square error. So let me define what mean square error, and then talk about this bias variance decomposition of this. So we called so the mean square error. So MSE is defined. MSE of an estimator we had is defined to be the expected performance difference of this versus the actual quantities that we're trying to estimate, right? So this is a mean over the data, and square is a loss function, and the expected loss function of this estimator, and is what we call mean square error. And this always can decompose into square bias plus variance by simply subtracting the expected value of v hat plus expected value of v hat minus v pi, right? And you can rewrite this by expected value of v hat minus ev square plus expected value of ev hat minus v pi squared that's outside, and then there's a cross term, right? So this is 2 times expectation of v hat minus e v hat multiply with e v hat minus v pi, right? And since the only randomness inside this expression, since this is fixed, right? And the only randomness is this term, and this expectation is taken over this v hat. So of course, once you take the expectation, and then this term will become 0, and the cross term becomes 0, and it remains is just by definition the variance of estimator v hat and the bias square of estimator v hat. Okay, so these are how we define the bias variance trade-off, and this is always like this formula is true for any input input estimator we had. Okay, so now let's analyze the direct method from the for the plugin estimator, so that we can compare their performances. Yeah, before that, so let me recall the MSE of DM in this special case of multi-arm bandit, right? So in for IS, so in simple multi-arm bandit, MAB. So recall that there are 3 parts of the variance that we have derived for IS as variance. So the variance of the importance sampling estimator. So notice that the variance is equal to MSE, right, of V hat IS. Why is that? Because this is an unbiased estimator, right? So that therefore the square bias term is 0, right? So we could so remember in the contextual case there's 3-term decomposition, and the first term is due to the first term is due to the randomness in the reward itself. So sigma square A, right? So I'm just throwing away that S parameter. So this is a variance due to the reward itself. And then there's terms that's due to the randomness of the policy, right? The randomness of the behavior policy. So this will be the variance of the behavior policy of pi A over mu A multiply with the expected reward. Right, so this is a randomness over A, where the randomness of the reward itself is expected out, is averaged out, right? So the third term is coming from the variance of the context, and the multi-embedded we don't have the state distribution or context, so that term is 0, and this is the final bound that we final expression of the MSE of the importance sampling estimator that we get. So let's call this. Let's call this V1. Let's call this V2, right? So these are two quantities that neither one of them can be used to bound the other. So V1 is not necessarily larger or smaller than V2 because it really depends on the scale of this this R, this expected reward and its corresponding variance. Now let's analyze the direct method. So first of all, the V hat dm is equal to A pi of A R hat of A, right? Pi of A is so let's start by calculating its expectation to see whether it is biased or unbiased. So this is the same as sum over pi of A, expectation of R hat of A. So what is this R hat of A that we're using? Simple plugin, right? So we simply plug in. So this is expected value of 1 over NA sum over Ri indicator of AI is equal to A. And there's another additional indicator indicating that NA is strictly larger than 0, because otherwise we're simply returning 0. Okay, that defines the plugin estimator. We basically need to like deal with these cases separately, deal with the two cases separately. The case when NA is larger than 0 and NA is not larger than 0, when NA is equal to 0, and when NA is equal to 0, then we're getting 0, obviously. And when NA is larger than 0, and the first term is the right expected value, right? So this is equal to sum of A pi of A probability of NA being larger than 0 and expectation of 1 over NA sum of Ri indicator of AI is equal to A given NA is larger than 0. When that happens, this is a bias estimator. So ultimately we can remove this and then replace this with R of A. Right. So this is different from the this is different from the true value that we want, right? The true value that we want is doesn't really have this probability, right? In other words, we can write a bias of V hat dm to be the difference between V expected value of v hat dm minus v pi, and this gives us summation of a pi of a r of a, but probability of NA larger than 0 minus 1, right? So chances are, like, if this mu is exploring, as the number of data points n gets larger, every action will be visited at least once, right? So this is this is 1 minus probability of not choosing mu of 1 minus mu of a. So this is a probability of not choosing a for indefinitely, right? So so this is equal to that. So as n goes to infinity, this certainly converges into 1. Therefore, the bias converges as n goes to infinity to 0. Okay, so even though this is a bias estimator for finite sample, but the bias is somewhat small, and depending on how this mu a is close to 0, it could go to 0 exponentially as n gets larger. Yeah, now let's calculate the variance. Yeah, so I'm doing all these statistical analysis that might be like somewhat easy and trivial for those who have statistical background, but for computer scientists starting a PhD and wanting to do this theoretical research, it is helpful to go over these simple calculations as detailed as possible. So when you guys start doing the PhD level research, it's always a good idea to err on the more rigorous side and to keep writing down like simple equations and make sure that everything is make sure that you understand every single step, right? So that is a motivation for me to go over this seemingly pretty tedious calculations that you could potentially do yourself, like in the lecture together. Okay, so I'll do this, and then for even more complex calculation, I'll skip them and maybe ask you guys to do them in the homeworks. So now let's calculate the variance. Right, so let's get rid of that. So the variance of the multi-arm banded estimator for right, so this is what it is, and let's apply the law of total variance, right? By applying, we can decompose this into the expected variance and variance of expectation. So what we're conditioning on now this time. So we basically want to condition on this this NA parameter, right? So this is a variable. Like once we condition on them, and across each A, things become independent to each other, right? So let's consider on condition on NA for all A inside the action space, and then plus the variance of expectation R cat of A given NA, right? So like a little bit about conditional expectation and conditional variances. When you are conditioning on something, then that something is what you take what you consider to be the random variable that's outside, right? And this becomes this conditional expectation becomes a function of its input, and inside this conditional expectation, you're getting rid of the randomness on the left hand side of the bar, and then this conditional expectation itself becomes a random variable, and the variance is taken over that random variable that you're conditioned on, right? So yeah, there are more formal explanation of this in the measure theoretic treatment of probabilities, but this is how you should remember it. Whenever you're conditioned on something, then this is a function of that something, and that's considered fixed. But in the outside, there's another operator that deals with the randomness of what you have conditioned on. Okay, so now let's let's work out what this is. So now that you have given this NA, right? Like I said, that condition on NA, the different R hat of A becomes independent random variables, and then you can simply exchange the order of the summation and the variance. So you got the summation over A, then the variance of the individual individual R hat of A. Given NA. Okay, and the second term simply becomes simply becomes right. So there are basically two cases. The first case when this NA is 0, right? The second case when NA is not 0. When NA is not 0, this expectation is when NA is not 0, this expectation is unbiased. Then you get R of A. But when this NA is 0, then you actually get 0, right? So we can add an indicator here indicating NA is larger than 0. Right? When it is 0, it's actually 0. So this is a random variable. It's actually a Bernoulli random, very similar to a Bernoulli random variable that takes its value that takes its value of whether or not this NA is 0 or not. And we've seen previously that this is a tiny probability that this as n gets larger, this NA is still 0, right? So now let's deal with this both terms separately. And first of all, what is what is this? What is this? So let's work out this expectation. This expectation has two cases. When this NA is 0, then R hat A is fixed at 0. So there's no variance, right? So when NA is not 0 and this when NA is not 0, then this R this R hat is equal to since this is expectation formula, this plugin estimator, and we know that by the independent random variables, the variance becomes 1 over NA, and then variance of the individual individual R individual Ri, right? So when you choose action A, and this is actually, according to our notation, sigma square given A, sigma square of A, right? And we'll need to add an indicator of NA is larger than 0, right? And this is smaller than say E of summation of A 1 over NA plus 1, right? Sigma square of A. So notice that this NA is a binomial random variable, right? So the expectation of 1 over NA square, we can actually write it down. Yeah, I think I missed this pi 1 square that's outside. Yeah, I missed the pi A square. So there need to be a pi A square, right? So this is NA is a binomial random variable of n copies with that p parameter being just the mu a. Right. So we can rewrite this into first of all, we can drop this indicator because we're taking upper bound, and this becomes a summation of a pi a square over n plus 1 mu a and sigma square of a, and 1 minus mu a to the power of n plus 1, right? So again, this term goes to 0 exponentially as n gets larger. And for the second term, we'll just obtain a crude upper bound, right? So let's use the R max upper bound to bound the expected value of a, add a square here since this is variance, and then multiply with a probability, of exists at least some a where NA is larger than 0. So clearly, this term goes to 0 as n goes to infinity, and this term goes to 1 as n goes to infinity. And what we are left with is a quantity that looks like that, right? So let me rewrite it in a different color so we can see it. Right. So conclusion, we get that as n gets really large, and this is roughly sum over a pi a square over mu a 1 over n plus 1 sigma square of a. Right, and as n goes to infinity, what is this? This is just expected value, right? So you can add a square here, and then make this mu a also here, and this is just the 1 over n, the expected value of rho square sigma square. Yeah, and I argue that this is just V1, right? This is the same as V1. Right, so now we have a comparison between the direct method and the importance sampling. So the direct method in this case is asymptotically biased. So for finite sample, it could be biased, but as n goes to infinity, it like the variance is smaller than that of the importance sampling because it is only the first term. And the second term, the variance that are coming from the policy itself is eliminated by considering only the regression estimator. Okay, yeah. There's something between called a weighted importance sampling estimator, and the weighted importance sampling estimator it's also a bias estimator. It provides something in between, like the importance sampling, the naive importance sampling, and the model-based approach. So the idea of weighted importance sampling is self-normalization. So we had WIS. This is equal to so instead of 1 over n. So now I'm summing over the importance weights. And then and recall that rho I is pi of ai given si and mu of ai given si, right? So the motivation behind this weighted importance sampling is to somehow correlate the numerator and denominator in ways that are related to the importance sampling while still retaining the good property of the importance sampling estimator that doesn't require you to model the reward as a function of state and action. It doesn't require you to have access to a realizable function class. And why is this okay? So if we take the expectation of the sum of the importance weight, and this is mu right? And by the definition, and this becomes a sum over mu AI SI pi AI SI over mu AI SI. These two got canceled, and this is a summation over A, right? And since pi is a probability distribution, this becomes just n, right? So weighted importance sampling has a numerator and denominator both converging to the right quantity. Therefore, like we had WIS as n goes to infinity converges to the true value. It is slightly biased, but it has a lower variance compared to the importance sampling, right? So let me show you some experiments. So in this experiment, we can see that when the number of data points is small, it is better to use the IS. IS is better than the regression estimator. So this REG is DM. And as the number of data point gets like larger towards n goes to infinity regime, then the regression estimator is something that's that achieves the Kramer-Rao variance lower bound, right? So it becomes the optimal bound. And I'm also plotting this V1 and V1 plus V2 as a reference. So you can see that the V1 plus V2 like matches what we calculated for IS, not surprisingly. And V1 only is what this regression estimator converges to as n goes to infinity. On the other hand, like the regression estimator is actually quite bad, like with a relatively smaller number of data points, right? So it can be like twice as bad. On the other hand, the weighted importance sampling seems to be getting the best of both worlds, and improving over NS like throughout for all regimes of n. On the other hand, this is not always the case, right? So on a different data set, you can see that in this case, the weighted importance sampling and importance sampling, they behave very similarly, and the variance for weighted importance sampling doesn't really vanish as n goes to infinity, right? So this motivated us to consider whether there are like better estimators that can like maybe do well, like with all parameter regime with all n. Okay, so we'll talk about that after we take a 5 minutes break. So let's resume the lecture at 2:21. I'll see you guys in 5 minutes. Okay, everybody, welcome back to the lecture. Let's resume the lecture. Um, yeah, so far I've shown you three different estimators: importance sampling, weighted importance sampling, and regression estimator. And here are their relative performance on the data. We formally analyzed the behavior of these estimators to see that importance sampling um, requires less of an assumption, but it has higher variance comparing to the regression estimator, at least asymptotically. It has some benefits over the model-based approaches when the model is incorrect. So in this case, model is correct, therefore asymptotically it is better. But when the model is not correct, then the importance sampling doesn't have that asymptotic bias. Meanwhile, the regression estimators will have some bias. For small sample size, sometimes the importance sampling could have a could be better, and in almost all cases we can improve the IAS with a weighted importance sampling. Yeah, when we measure everything by MSE, right? So this is n times MSE, so we are only computing the constant factor in front. Okay, so the the next thing that I want to tell you about is the so-called W robust estimator. So the idea is that well, sometimes like I have a good regression estimator that's given to me, maybe estimated from a different data set. So can we make use of this to reduce the variance of the importance sampling estimate? Right. So using it as a baseline in the same way that we dealt with policy gradient. So remember that when we derive the policy gradient, we talk about how we can use a function value approximation on the side and then substitute that to bootstrap the policy gradient. And we started by talking about something simpler with a fixed function that depends on the state as a baseline, right? So W robust estimator is really just very similar to that. So we had DR. It's essentially a version of importance sampling estimator, but the difference is that so now we're back to the contextual bandwidth, right? Back to the contextual bandwidth with SI, AI, RI, or in some places we'll have XI, AI, RI as your data. So the and then we're given the regression estimator R hat of SA for any SA. You can evaluate this. Then what the OPE estimator for policy pi that is doubly robust is the is just not AI, but rather something else. So this gives you the baseline. And then we're estimating the difference from the baseline by importance sampling. This will be this R hat of SI AI. Okay, so that specifies the W robust estimator. So let me explain to you what this is and why does this work. I basically have add a baseline and then subtract something that's in expectation the same as the baseline, right? So these two together, I'm using importance sampling to estimate the bias, to debias this baseline, to estimate the difference between the baseline to the true value. Why does this make sense? And this makes sense because I noticed that in this R hat, like it depends on AI. So if this R hat of SIAI is somewhat correlated with R of I, then we can make use of this to reduce the variance of this original IS estimator, right? So it is unbiased because we can easily calculate this variance. So notice that in this case, R hat is not a random variable. R hat is fixed, given, and may be estimated from a different data set. And we can clearly see that this is unbiased because the expectation, this becomes the expectation of SI drawn from this minus E, and then this is a conditional expectation over A under this and multiply with rho, and rho is a pi of ASI over mu of ASI, right? These two got canceled out, and then you got this expected value of Ri given S and A, given S on the outside, right? So and this is only the Ri part, and the other part will be the sum of A pi of ASI subtracting R hat of SI A, and this is the same as that. This is the same as that. Therefore, these two got canceled out, and then we end up getting just the correct value, which is the mean of the IPS. Importance sampling equals to B of I. Okay, so the doubly robust estimator is also unbiased. It is using importance sampling to estimate the bias of a baseline regression estimator, right? So in this way, so this is a systematic way for you to combine the regression estimator with a baseline and with the hope of getting the best of both worlds. But does it work? Does it really get you the best of both worlds? So first of all, like the doubly robust has a longer history in statistics and econometrics. Like it's mostly used in the semi-parametric efficiency literature for say causal inference and average treatment effect estimation when there are nuisance parameters that you do not care about and still want to get the parametric rate when you have a non-parametric function as part of the estimator. So in those cases, the key challenge is typically that you are dealing with observational data. You do not know how those actions are taken. You do not have the true value of the propensity score. So in other words, in those cases, you have to define estimators by estimating the propensity score and also estimating the regression function at the same time, right? So the version of the challenge is unknown mu I, right? So mu I is mu of AI of SI. So we do not know what the probability the logging policy has taken, and this is often true in reality when the people who log the data, like it's not really randomizing, or they are randomizing, but they but you simply did not record what the what the probability that you have used to sample this AI, right? So in this case, you have to somehow replace this with mu hat of with two input SIL of AI, right? So you can like sometimes come up with estimators for this this mu I by looking at which action that you have taken, and then try to use, say, some probability, some family of probability distribution to describe this, right? So and then you run into the same challenge of what function class to specify, because it is unclear whether this mu hat, as the number of data points goes to infinity, will converge to mu, and just in the similar way of whether this r hat will converge to r. So you do not know, unclear whether r hat SA will converge to r of SA, and mu hat of SA will converge to mu of SA, right? So the doubly robust estimator in the model in this setting simply replaces this previous formula, with by replacing this mu I with mu I hat. So let me write it down. So I'll just use a shorthand of r hat pi SI, right? So this should be consistent with our notation in the reinforcement learning part of the lecture. So when we have pi over here, it says that we are choosing this action according to policy pi, and then I'm then using the importance sampling estimator of pi AI SI over mu hat SI AI multiply with Ri minus R hat Si AI. Right. So this will be the version of the doubly robust estimator when we are also when we also need to estimate the propensity scores. Okay. So one attractive feature for doubly robust estimator is that it is doubly robust. And why is that? It is robust to the model misspecification of either this mu hat function or the r hat function. Right. So let me explain that. So if either mu hat and r hat is, or r hat is consistent. Consistent meaning that as n goes to infinity, they converges to the true value. Then v hat dr is consistent, converges to v hat pi. If either mu hat expected value of mu hat is equal to mu, or expected r hat is equal to r, then v hat dr is unbiased, right? So these are what we call double robustness. So we have already seen in the previous slide that when this r hat is incorrect, right? When this baseline is arbitrary, right? So we're not making an assumption on r hat at all. Then we have seen that the expectation of this is actually is actually correct when this mu I part is chosen to be the correct value, right? So that should be clear that as n goes to infinity, is this mu I converges to the correct value. So this is still the same phenomena that you should observe. On the other hand, when this mu hat is something that's way off, when this mu hat like is inconsistent, then provided that r hat is consistent, then this is also fine. right? Why is that the case? So notice that there are two terms. In the first term, if r hat converges to the true value, then the first term alone will give you the first term alone will give you the correct value. And the second term, like you don't need this mu hat to be accurate at all. If r hat of SA is converging to r of SA, then r of SA is equal to its expected value of Ri given as AI, right? Then this term has zero mean. So when we average over n copies of such terms, we'll end up getting zero, right? Well, by law of large numbers, this will converge to zero. So these are the reason why the doubly robust estimators are doubly robust, because it is robust to two different ways of model misspecification. If either you only require one of them to be consistent in order to have a consistent estimator. Secondly, like whenever this v hat and mu hat and r hat, they are consistent and they converges to their true value at a rate that are sufficiently fast, then you can show that this v hat dr is asymptotically efficient. If the product of v hat minus v multiply with r, r hat minus r product with 1 over mu hat minus 1 over mu, if this goes to 0 at a rate that is little o 1 over little 1 over 1 over square root of n. So if it goes to 0 faster at a rate than 1 over square root of n, then this implies that the doubly robust is asymptotically efficient. And in the previous example, it has variance that matches the regression estimator, right, with only v1. Okay, so in particular, yeah, I think you actually need this separately. You need both of this to be 1 over n to the power of 1/4, right? Yeah, or alternatively, when this mu hat is actually perfect, then you only need this r hat to be like little 1, like before you can get asymptotic efficiency. If mu hat is equal to mu. Yeah, so at least asymptotically doubly robust estimators are good, but like sometimes when the model is hugely misspecified, this finite sample performance can be quite bad, and in fact when you choose this r hat to be positively correlated with the existing randomness in the importance weighting, then the variance of the doubly robust estimator can actually gets larger, can actually get quite a bit larger, right? So this is like not very satisfactory. In a paper that I wrote a couple of years ago, I've shown that like if you are not willing to assume that you have access to a function class that is realizable, that's going to give you a consistent estimator of r, the expected value of reward given state and action in a contextual bandits model, then you cannot actually improve over the importance sampling estimator, right? So this is the same as that 3-term decomposition, but I merged the second and third term together into this. Yeah, since I'm just taking this Rmax. Yeah, and the second term is always smaller than the third term, so I can always do that. And what is lower bound? So this is a lower bound that applies to any input, any function of the input data, right? So I've defined a family of problems, and that's fixing the I'm taking the worst possible problem within this family that's specified by two functions, the sigma square and R max, right? So I'm only changing the reward distribution, and well, for this family of modest problems, no estimators can actually do better than importance sampling. So this shows that the IS is optimal in the worst case when we do not actually have anything, have access to a good regression estimator that could be consistent, right? So in this case, it cannot do better than the naive importance sampling. Like this appears to contradict with classical optimality theory. Like if we look at the asymptotic Cramer-Raw lower bound, this is what any estimator, what an efficient estimator like could potentially achieve for every for every problem separately. So when we take the maximum over the family that I considered in the previous slide, it gives me this quantity. And when I compare to the lower bound, well, the second term is smaller, right? The second term is smaller by a Jensen's inequality since the square is inside this expected value, right? But how could this be? Like, how could how could there be efficient estimators that achieve this asymptotic limit while beating like my lower bound? Did I prove it wrongly? It wasn't actually the case. So everything's hidden in the assumption. This table summarizes everything. So basically, you need to make some mild assumption about the regression estimator before you could find something that achieves the Cramer-Raw lower bound. So in particular, at least you need to assume that this regression function is differentiable, right? If it is not, then there are going to be other structures that you can capture to design this regression function. So in short, if you have access to a good model, then use a model. It will give you like a lower variance, at least asymptotically. If you are not willing to make such assumption, or like it's just impossible to model this complex physical process of reward given state and action, then the importance sampling cannot be improved beyond the universal constant. Okay, so how do we still make progress? So what we did in that paper is to propose a different approach of making use of a given regression estimator without worrying about how good or bad it is, and then to appeal to bias variance trade-off. So the idea is simple. So for every data point, like we should use like either the regression estimators to provide us this imputation, right? Or use the either importance sampling or inverse propensity score or doubly robust estimator to provide that imputation, right? So if we use IPS, then recall that this R hat of S, I, and A will be, this is AI, will be mu I of Ri, and everything else is 0. If we use a doubly robust, yeah, this is over OA, so this is S dot. If we use doubly robust, then this will be this will be R hat S A this will be R hat SA for all other A, but at AI, so this will be mu I times Ri minus R hat S R hat of SA plus R hat of SAI plus R hat of SA. Right, so these are the imputation view of the importance sampling of either the importance IPS and W robust, and in the other cases you just use a full regression estimator. So so why like what is the intuition behind this? So the importance sampling is bad and it has high variance is only like mostly because the importance weight can be large. So when the target policy chooses an action with significantly larger probability than your login policy, then well, in this case, the large importance weight will lead to large variance, which result in the poor performance of the importance sampling estimator in practice. But these are things that we can observe, right? If we observe that this quantity is small, then let's use importance sampling to get the benefit of unbiasedness and assumption free. And whenever this importance weight is large, then we will resort to the regression estimator. So even if the regression estimator is bad, then the largest bias that we incur from this part of the decision will be like beneficial, since the variance is going to be too large if we use importance sampling, right? So essentially, this is different from doubly robust in that it is appealing to bias variance trade-off, and then we're switching back and forth between the regression estimator and the importance sampling idea, right? So we can analyze this, which I won't bore you with the details, but we can analyze this this estimator and then get away with not depending on the largest importance weight. Right. For instance, then in the worst case, there might be some actions that the target policy will take, but the login policy is taken with arbitrarily small probability. In which case, this rho square term in the expectation will lead to a heavy-tailed distribution, so you cannot actually bound the MSE at all. Right. With switch, then we have an arbitrary truncation with this parameter tau that's set over here. That eliminate this issue of high variance at the cost of introducing a little bit of bias in the second and third in the third term, right? The second term is the variance from context. The first term is the variance from the distribution. The reward distribution itself that is the improved version of the variance of importance sampling. Okay, and we also like had a nice way of choosing choosing the optimal parameter in the data dependent fashion. Yeah, I'll just leave this slides here in case you're interested in how this works. And when we apply this to a bunch of data set and the performance of the switch estimators, it's almost always better on all data sets comparing to the baselines. Including the doubly robust estimators, and in particular when we add label noise, when the reward itself is actually noisy, then you can see that the switch estimator beat everything else by much larger margin. Yeah, I haven't explained what this figure is plotting. So this is plotting the CDF of the relative error versus the importance sampling estimator. So the closer to the top left corner of these curves, the better, right? And these are plotted over the cumulative distribution function over 10 data sets. Therefore, it looks like it's something that's increasing because it is a CDF. And the smaller, the more on the left these lines are, like the better. Because that is saying that overall on all 10 data sets, you will have a much smaller variance, much smaller mean square error. Okay, so I'm gonna wrap up. So in today's lecture, I talked about the off-policy evaluation problem for contextual bandits and for multi-arm bandits. I talked about multiple estimators and ideas behind each estimators. I talked about the direct method, which uses a regression model. I talked about importance sampling, which is more non-parametric, that makes use of the randomness in the login policy to construct unbiased estimator, regardless of whether you can model the process or not, right? And it can be improved into the weighted importance sampling. I talked about the idea of doubly robust by adding a baseline and use a baseline to denoise and to reduce the variance of the importance sampling approach. And then I talked about a complementary idea of introducing a baseline by using that baseline for bias variance trade-off. So that's switch. I also talked a little bit about an optimality theory on like whether an estimator is optimal really depends on what you have access to. And in practice, however, like making use of the regression estimators in one way or another, either using the doubly robust or using switch or using both of them together, like is a good idea because it will almost always substantially improve over like either using DM alone or using the importance sampling approach alone. Okay, I'm gonna stop here and we'll talk about the off-policy evaluation in reinforcement learning by generalizing these ideas and talk about the key challenges over there in next Monday. All right, yeah, thank you all for coming. Bye.